FPGA design tools must provide a design environment based on digital design concepts and components, gates, flip-flops, multiplexer, etc. They must hide the complexity of placement, routing, and bitstream generation from the user. Manual placement, routing, and bitstream generation is infeasible for practical FPGA array size and circuit complexities. There are way too much logic to manage, and it will be too hard to make changes. That means that to program an FPGA, we need hardware description languages to help us in describing the desired system behavior. These languages are used to specify functionality of logic at a high level. Examples of these are VHDL, which stands for VHSIC hardware description language, where the VHSIC itself stands for Very High-Speed Integrated Circuits, and simply Verilog. Once that we have our input specification, we need tools to validate it. Validation is a very important phase. Through high-level simulation, we are going to be able to catch specification errors. Furthermore, we can use to verify pin outs and connection to other system components. And at a lower level, to verify mapping and check performance. At this point, we have a specification of the system we are willing to implement. We have been able to validate through high-level simulation, but we do need something that is going to allow us in generating the necessary configuration bitstream file. This will be done, first of all, through the logic synthesis, which can be seen as the process of compiling an HDL program into logic gates and flip-flops. I don't want to guide you through this step in details. We may need a course just for this, but I'd like to give you an idea of what is happening behind the scene to better understand the complexity of the process carried out by the tools you are going to use. So, right now we have a bunch of logic gates and flip-flops, and what we are looking for is in finding out how to implement these elements within the given architecture we are working with. In other words, we are interested in knowing how to map the logic onto the elements available in the implementation technology, LUTs for Xilinx FPGAs. Because of this phase is called technology mapping. The output of the technology mapping phase is a netlist. Therefore, we can see the technology mapping as the process of describing a circuit with a netlist that consists of only gates belonging to a specific technology library. Now, at this point of the process, we move from a pure description of our specification to something which is starting to bind into the underlying hardware that will be used to implement it. We have a netlist defined by elements of a given library, but still we don't know exactly which instance of an element will be really used onto our hardware device. In other words, we may know that a certain part of our input specification will be implemented with a certain number of LUTs, as an example, but we don't know which LUTs are going to be used on our FPGA, and this is something which is unacceptable. To solve this issue, we need to go through a new phase of our process. We need a placement and routing phase. The placement and routing phase assigns logical blocks to function, and by doing this, we are going to know exactly which element on our device will be used to implement which component in our specification. Once that the elements are placed, we need to make wiring connection. Data has to move. We need connection in between elements to allow this. Obviously, things are not easy, and the placement and routing are not two subsequent separated processes, but they are strongly connected. A decision on where to place an element will have a huge impact on the routing, and vice versa. Once that everything has found an implementation, we need to verify a few more things. One of them is the timing. We need to go through a timing analysis to determine delays because of the previously taken decision, to look at critical paths and ways to improve them. At the end of this process, if everything is respecting the system requirements, we can generate programming files. This is the phase used to generate the well-known bitstreams to be loaded into the FPGA configuration memory for configuring it.